Hey class. All right, today we're going to be going over lecture, what are we at now? 19. Holy smokes. We're already over halfway. I think there's 36 total lectures. So we hit halfway last time. All right, lecture 19. So we're going to move on now. We did like the last 4 lectures are very much mass calculations. We're moving on to gases, but you're going to see how, maybe not in this lecture, but in the next lecture, we'll probably connect it to what we've been doing before too. So let's go ahead and get started on it. Just as a review from last lecture, go ahead and try and answer this question here. All right, so the question is, ozone is formed in the upper atmosphere when ultraviolet light splits a molecule of oxygen into 2 oxygen atoms. And these atoms then react with two other molecules of oxygen. Okay, so ozone here is the product. So you take oxygen and you form ozone through this reaction. So a balanced chemical equation would have 3 oxygen molecules form 2 ozone molecules. And we have a delta H of a positive 286. So a positive delta H indicates endothermic reaction. And because it's an endothermic reaction, that means that heat is actually going into the reaction, so it's a reactant. And the question says, how much energy is absorbed when 50 grams of ozone are formed? Okay, so we can start with grams of ozone. Again, this is the kind of the heat map that we talked about last time. We can go from grams of A to moles of A, and then over to heat. Okay, and this is energy too. So the question is how much energy or how much heat is absorbed. So ozone is going to be our A in this case. So we'll start with grams of ozone. Okay, so this is 50 grams of ozone here. Then to convert from grams to moles, we're going to need the molar mass of ozone. So the molar mass of oxygen is 16 times 3 would be 48. Okay, so this is grams of ozone and moles of ozone. Okay, and then to get from moles to heat, we're going to use the heat conversion using the coefficients from the equation. So 2 moles of ozone require 286 kilojoules of energy. So run that calculation and you get 149 kilojoules are required to produce 50 grams of ozone. Okay. All right, so now we're going to be moving into gases. A lot of reactions, and we've already seen a bunch where reactants or products are gases. Okay, it's very difficult to measure the mass of a gas, right? You can imagine that'd be hard, and but it's easy to measure the volume of a gas. So instead of questions that say you have 3 grams of hydrogen gas or something, it's more likely to report that in a more real life application is a volume. So you might say you have 1 liter of hydrogen gas or something in a balloon or something like that, where it's easier to measure the volume. So for stoichiometry purposes, right, we've gone from, let me see how much stuff is on this slide. Okay. All right, so for stoichiometry, it says we'll convert from volume to moles of gas. We need to understand how the volume of a gas depends on pressure, temperature, and moles. Okay, so let me draw out kind of the map that we've used thus far, right? So we've said we can go from moles of A over to moles of B, right? And we can go between grams of A and moles of A. Then we can also go between moles of B and grams of B. And this is pretty much where we've stayed for the last 4 lectures, right? We've gone from grams of A to moles of A, then over to moles of B, then to grams of B, right? We've done that like a billion times. We can also go from moles to molecules of A, right? Okay, we can go from moles of B over to molecules of B. All right. Okay, so just as a review here, molecules to moles would be using Avogadro's number. From grams to moles, that'd be the molar mass, and that's true on both sides. And we have Avogadro's number. Okay, but when we're dealing with gases, it's very hard to measure out molecules of a gas. It's hard to measure out molecules of anything. But it's also very hard to measure the mass of a gas. So what we need to be able to do is go from volume of A, if A is a gas, to moles of A. And if we need to convert from moles of B over to volume of B. Right, okay. So using gas laws, which we're going to be talking about mostly in the next lecture, we'll be able to convert from volume of A to moles of A, and you'll see an equation, it's PV equals nRT, okay? And that'll be the equation that will allow you to convert from volume directly to moles, okay? We can also do, maybe you add this on the map, we're making a very full map here. So let's say you can go from volume of A to grams of A using density, right? We've done this before. That's more for solids though. So if you have a solid that's given to you in terms of volume, in order to get to moles, you would need to go through grams. Volume of B. Okay, so this is density. I just want to point this out because you may see this in a problem at some point. Hopefully what you can notice from this map though is that you need to get to moles, right? If you're converting from one thing to another, you have to go through the mole bridge, I like to call it. And you're going to be using mole ratios to do that, right? You've seen that. So if you have a gas, I should put here, this is for a gas. Up here, if you're going from gas to moles, or sorry, from volume of a gas to moles, you'd use PV equals nRT, which we haven't talked about yet, but we will. You can go from molecules to moles using Avogadro's number. You can go from grams to moles using molar mass, and you can go from volume of a solid, okay, over to moles by first going through grams using the density, and then going from using the molar mass to get to moles. Okay, this is a solid. Okay, so there's a very complete map. Write that down and probably make it a lot nicer than mine looks. But hopefully you can be using that as we go forward to understand some of the problems. Okay, so different properties. We have 4 properties that we can measure with a gas. So you have a pressure, okay? So this is going to be the force that the gas pushes, exerts on the walls of something. So if you're blowing up a balloon or something, right, there's a pressure of the gas inside the balloon that's pushing against the walls of the balloon to keep it wide, right? All right. And we'll be talking about different units that are used for pressure. Unfortunately, there's like a ton, right? These are 5 of some of them. There's a bunch of them. And we'll probably use mostly just these 5. And the conversions for these are given on the equation sheet. So don't need to memorize the conversions, but we are going to kind of talk about what each one is. Volume is generally given in terms of the metric system, so liters or milliliters or centimeters cubed. An important thing to know is that 1 milliliter equals 1 cubic centimeter. So if something is reported, sometimes a problem will report a unit in a cubic centimeter, You can just instantly convert that to a milliliter if you want. Like by definition, cubic centimeter is equal to 1 milliliter. That's how they came up with the milliliter, or maybe that's how they came up with the centimeter. I don't know, but that's the definition there. Okay. Temperature, usually we have seen it in Celsius, and you still might see it in Celsius in the problems because it's just a lot more common to measure things in Celsius. But now we have this new unit, which is Kelvin, okay? And for a lot of the gas equations, we have to use Kelvin. The reason is Kelvin temperatures are always positive. And if you throw in negative numbers into the gas equations that we're going to go over, it messes up your answer. So you can't use Celsius. You need to use Kelvin. So 0 Kelvin, this is kind of interesting, but 0 Kelvin is the coldest you can ever get, right? You can't go colder than that. So if 0 Kelvin is basically the temperature at which like something has molecules that aren't moving at all, right? So temperature is a measure of like the kinetic energy of molecules moving. So if you have something, if you're, I don't know, in a place in space that's so cold that molecules aren't moving at all or whatever, I don't know if I'm explaining it perfectly, but that's basically what 0 Kelvin is, okay? The reason I think this is cool, because you may not have ever thought that there is a bottom shelf for temperature, right? There is a certain point at which you can't get colder, right? You can always get hotter, though. You can add heat to stuff. I think this is cool because I guess think about it more of like a spiritual aspect. We're at BYU, we talk about these things. There's also like perfect darkness, right? There's a point at which it can't get any darker, but you can always add light, right? Same thing. You can get to a point where it's totally cold, and you can always add more heat. So I think that's kind of cool. Let that simmer in your heads and maybe keep you up at night, pondering the vast, I don't know, the vast implications of that or whatever you want to think about. Okay, moving on. Okay, okay, not moving on yet. Still talking about Kelvin. Yeah, it's always positive, and there's a very easy conversion from Celsius to Kelvin, which I think is also on the equation sheet. So even if a problem reports it in Celsius, you just need to make sure you convert it to Kelvin before you move on. Okay. Amount. So we've talked about moles before. Mass doesn't really get used, like I said, that much with gases. But it's usually going to be in moles that we'll be able to talk about gases. Okay, we will use moles. There we go. So again, I said it's very hard to count the moles of a given gas or something in a balloon just by counting. You can't really do that. But you could use the volume of the balloon and the pressure to figure out the moles. So that's what we're going to talk about, is figuring out moles or mass of a gas using things we can actually measure, like volume and pressure and temperature. Okay. All right, so talking about pressure, again, pressure is always just a force over a certain area. So if a gas is exerting a certain force, right, if you have this balloon, okay, and you have little gas particles in here that are moving around, right, they're going to be bouncing against the wall of this balloon, exerting a tiny bit of force, right, each one individually, but as a whole, they're going to be exerting a decent amount of force to keep that balloon open, okay. So units for pressure, 1 atmosphere is basically the pressure at sea level. So everything's kind of standardized to that. And this is 760 millimeters of mercury, which we'll talk about what that means in a couple slides. You have 1 atmosphere also equals 760 torr. So torr is kind of just another name for millimeters of mercury. It's shorter, easier to say. But I mean, you can kind of tell from this that 1 millimeter of mercury is going to equal 1 torr, okay? All right. The other one we're going to talk about is pounds per square inch. That's what PSI stands for, pounds per square inch. Okay, and then 1 atmosphere would equal 14.7 pounds per square inch. PSI is a very common pressure, especially in the United States. And then we have 1 atmosphere equal to 101.325 kilopascals. Okay, so Pascal is also a term or a unit for pressure. And again, it's kind of complicated. There's a bunch of different ones, but you should be comfortable converting right now between different units. And you know, you have these equalities right here that you can use to create conversions and do conversions if you need to in a problem. Okay. All right, so atmospheric pressure, talking about what atmospheric pressure is. Sometimes people haven't really thought about that. It's kind of a weird concept, but there's a lot of gases in the atmosphere, right? So the atmosphere surrounds the Earth, right? So you have like atmosphere surrounding the Earth. Gravity is holding certain gas particles on the or towards the Earth, around the Earth, okay? And so although gas doesn't really seem like it, gas does have mass, right? It's matter, it has mass. And so if you're standing here on the Earth down here, you have all this gas that is pushing down on you, right? Because you have gas particles floating around that the Earth is pulling towards it with its gravity, and those are pushing down on you, right? And that's what this is. Atmospheric pressure is just basically gas particles pushing down on you, down on the Earth, right here on the surface, okay? So you can imagine if you have a mountain right here, and you're standing at the top of the mountain, you're going to have less, right? So the closer to the Earth, the more gas particles you're going to have, right? So it could be like something like this. Then as you start to go away, it starts to thin out, right? Because the gravity has less of a hold on the gas particles. So when you're up here, there's going to be less pressure pushing down on you because you have less gas above you, okay? So that makes sense. This is also why you might wonder, you know, at the top of a mountain, it's super cold, right? Even though you're closer to the sun, let's say the sun's right here. Give it some shades, of course. Okay. And if you're on top of the mountain, you're closer to the sun, you'd imagine you'd be warmer, right? Well, the sun is very far away, and really what's happening is as you move to the top of the mountain, you have less gas particles around you. You can think of the gas particles as like a blanket. So the closer you are to the Earth, the thicker the gas particle blanket. And the thicker the blanket, the warmer it's going to keep you. So there's more heat held in close to the Earth. As you get far away, it's a very thin blanket. And so since it's freezing cold out in space, even though the sun is out there, right? The sun, really the heat we get from the sun is mostly the rays coming in and the heat getting trapped close to the Earth. So the further away you get, the thinner blanket you have, the less pressure you have, and that's why it's colder on the tops of mountains. Cool. Okay, so talking about atmospheric pressure here. So we have 1 atmosphere at sea level. So that'd be, let's see, down here, down at sea level. Up on the mountain, you can see that the pressure is less, and I just kind of talked about why that's true. Lower at high altitudes, it obviously depends on the altitude and the weather, and higher on a rainy day than a sunny day, probably because there's more, I haven't really thought about this much, but you got more water in the air, it's probably more pressure pushing down, more mass in the air, I guess, on a rainy day. Anyway, you don't have to remember those things. You do need to know that pressure is lower at high altitudes and higher at sea level. That's probably important, but the rainy day and sunny day stuff and all this stuff isn't really that important, okay? Okay, so this is where we get to the millimeters of mercury, which seems like a funny unit, but really all that's happening is you have this vacuum tube, which means you have no air particles in here, so nothing occupying this space. and you stick this tube in a dish of mercury. There is, like we talked about, there's a certain amount of atmospheric pressure. So that pressure is pushing down on this liquid and forcing it up the tube. And when scientists discovered this, right, the distance between here and here was 760 millimeters. And so they called this pressure 760 millimeters of mercury. So this is a barometer, measures pressure. And so you could take this to different parts of the world. You could take it up to a mountain or something. If you go up to the top of a mountain, it's not going to have as much pressure pushing down. So you would have, the mercury wouldn't go as high in this tube. So you have a lower pressure. And that's how you kind of measure pressures, is using this barometer. I'm not really sure how modern barometers work, but I imagine they're not carrying around open dishes of mercury anymore. Yeah. All right. The reason they use mercury is because it's the heaviest liquid. Water is also liquid. You could technically do this with water too, but it would actually go up 407 inches if this was a vacuum tube. If you would just put like a normal tube in a bowl of water at home, it's not going to do anything because that tube isn't a perfect vacuum. But if you had a tube that had no air particles in it, which would be very hard to do at home, then it would fly up the tube and water would go very high. So it's not really practical to walk around with something that's 407 inches high as you're taking pressure readings. Okay. Okay, so kinetic theory of gases. You don't, I'm not gonna like ask you any questions on this particularly, so you can kind of just sit back and enjoy this slide. Just talking about behavior of small particles in the gas form, kind of how they behave. They move in rapidly straight lines. They have essentially no attractive forces. So we've talked about intermolecular forces like dispersion forces and things like that. But we're just gonna assume that they basically have no attractive forces between them, gas particles. So they're far apart, and the gas particles have small volumes compared to the volumes of the containers they occupy. For example, you might have this many gas particles in this whole container because they're moving and occupying it, but the actual space that the molecules occupy themselves, you can see, is quite a bit smaller than the whole container. Okay. And the kinetic energies are proportional to temperature. So the faster they're moving, the higher the temperature. So this is what I was talking about when I was talking about 0 Kelvin would be when these particles are not moving at all. Okay, that'd be totally 0 Kelvin. Okay. All right, vapor pressure. So this is kind of a concept you're going to want to understand. And I think it's interesting too. It'll explain some of the stuff that you've probably noticed before but didn't know how to explain. Okay, so molecules in a liquid have a distribution of speeds. So you've probably seen like distribution curves before, kind of like this, right? Where let's say most of the molecules are in this center spot. So if we're talking about speed, right, remember speed is related to kinetic energy, which is related to temperature. So if you have a cup of water and you put a thermometer in the cup of water, okay, the thermometer might read 23 degrees Celsius, right? That's room temperature. Okay, so you have a cup of water, stick a thermometer in it, it says 23 degrees Celsius. That means that most of the water particles are moving at 23 degrees Celsius. That's what that temperature reading means. But it does not mean that all of them are moving at 23 degrees Celsius. You have these different levels basically. So you might have, this might be 100 degrees Celsius up here, okay? And then you might have like, I don't know, negative 70 degrees Celsius. Okay, those numbers don't really matter as much, but basically what it's saying is that even if the average, or sorry, not the average, but the median temperature of the water molecules, or the median speed corresponds to 23 degrees Celsius, you're going to have some water molecules that are moving at 100 degrees Celsius or faster, And we know that 100 degrees Celsius is the boiling point of water. So if a water molecule is moving at 100, or if it has enough energy to move at 100 degrees Celsius or more, it's actually going to evaporate into the gas phase, right? So that's what's happening. So anything, right? If you have an apple or, I don't know, whatever you touch, right? Or stick a thermometer in the air, it's that thermometer is reading the speed. Really, it's the speed of the kinetic energy, but it's reading the temperature of kind of the average number of particles, gas particles in the air. Okay. That being said, there are some that are moving faster and some that are moving slower. Okay, so kind of with the water, what we're talking about is some molecules have enough kinetic energy, right, if they're over this divide here, to escape the intermolecular forces holding the liquid together. They have enough energy to evaporate, basically is what's happening, right? Then they evaporate, and then there's some of these that are moving slow enough that they actually condense back into a liquid. But there's kind of this equilibrium that's going on here, okay? So in a cup of water, you don't just have liquid water, right? If you put a lid on that jar, what you actually have is a bunch of liquid water and a small amount of steam or gas water in the cup. You notice this if you leave a cup open at room temperature for a long amount of time. I don't know, might take like a week or a month or something, but the water will actually evaporate, which, you know, before you may not have been able to explain very well if you don't understand this concept, because water boils at 100 degrees. So if you leave an open cup of water in your apartment or your house, technically, you know, it's not at the boiling point, so it wouldn't evaporate. But some of the water molecules will escape, and then out of that, some more will escape, and eventually you'll have all the water molecules actually boiling out. Okay. Okay, so the molecules that escape are in the gas phase, and the pressure that this gas exerts is called the vapor pressure. Okay. So the vapor pressure is the pressure that this gas exerts on the walls of the container. All right, that's what vapor pressure is. So the higher the temperature, obviously the more energy, and the more particles are able to escape the liquid phase. So if we look at this graph here in the top left, if the water is sitting at 23 degrees, this is your distribution. But if you add more energy and you have a higher temperature, let's say now the water molecules are sitting at this average temperature, your distribution is going to look like this. So you're going to have a lot more water molecules that are escaping into the liquid, or sorry, into the gas phase. Okay. So that means since there's more particles escaping, the vapor pressure is going to increase as temperature increases. And that's what we see on this graph. So let's look at water, the blue one here. So for water, as the temperature increases, temperature is on the X, vapor pressure is on the Y. As your temperature increases, okay, your vapor pressure also goes up, again, because you have more particles moving into the gas phase. And then what this horizontal line here represents is, this is atmospheric pressure. Okay. So now let's say we have this cup of water, okay, and it's exerting a vapor pressure out of this, over the top of the liquid here, basically. You have another pressure called atmospheric pressure that is actually exerting force on the water to keep it in the water phase, right? If there was no pressure holding these molecules together, they would just escape, okay? And they would boil, or yeah, they'd escape into the gas phase, right? They'd boil. So the water is basically pushing a vapor pressure out, and then the atmosphere is pushing it down, right? And a little bit escapes, a little water does at room temperature. Once the vapor pressure is equal to the atmospheric pressure, which is 760 torr at sea level, once these are equal, as soon as you go above that, the water basically wins, and that's what you call the boiling point of water, right? So the boiling point comes from vapor pressure. So if the vapor pressure equals the pressure of the atmosphere, right? That's the point at which something begins to boil. Okay, so for all substances, that's true. Okay, all right. So, and you can increase the vapor pressure by increasing the temperature. So in order to get water to boil, there's really two options you have. You can either decrease the atmospheric pressure, okay, till it is in line, until it equals the vapor pressure of water. If you do that, then the water boils. You can also increase the vapor pressure to equal the atmospheric pressure, and that's what adding temperature does. So when you boil water on your stove, all you're doing is adding enough temperature to where that vapor pressure equals the atmospheric pressure, and then it allows your water to boil off, okay? All right, so this is vapor pressure of water. This kind of is just pulled from the graph, basically. So the higher the temperature, obviously, the higher the vapor pressure. So you can see at 100 degrees Celsius, the vapor pressure of water is equal to atmospheric pressure. That's the boiling point. Cool, I think this is pretty sweet. We talked about that. Okay, so this is gonna be why, I think the next slide might talk about it. Boiling pressures change depending on your altitude, okay? So the boiling point of water, you can see, is actually at 95 degrees Celsius when the pressure is 630 millimeters of mercury, or torr. Okay, so let's see. We're not going to talk, we don't really have these examples, but increases when a higher pressure is applied. Boiling point. Okay, yeah. So the pressure cooker example here, sorry, I was trying to gather my thoughts. You maybe used a pressure cooker. I served a mission in Brazil, and they use them to cook beans. Beans need a lot. They need a very high temperature, or they need a long amount of time. You kind of choose, but pressure cookers allow water to get over 100 degrees Celsius. So let's just say you're at sea level and you're boiling pasta, right? Or you're boiling water, sorry, to make pasta, okay? And you throw your pasta in the water. That pasta is cooking at 100 degrees Celsius, right? As soon as this water gets over 100 degrees Celsius, it's going to be evaporating. So the water actually never gets over 100 degrees Celsius, right? Because if it did, it would turn to a gas and leave. So the highest you could cook that pasta is at 100 degrees Celsius. And that's because the atmospheric pressure is, 1 atmosphere, and the vapor pressure of water at 100 degrees Celsius is 1 atmosphere as well. So the only way to get water to actually get hotter than 100 degrees Celsius is to add more pressure. Okay, so now let's say you have like 10 atmospheres of pressure. Well, now in order for the water to boil, the vapor pressure of water needs to equal 10 atmospheres. And so you actually need to add in enough temperature to get this water to whatever, I'm just going to throw out a number, 300 degrees Celsius, right? Only at 300 degrees Celsius does the vapor pressure equal 10 atmospheres, and it will boil off. Again, I'm just using random numbers, so don't fact check me on this. Okay, and then the opposite is true at higher altitudes. So if you're at a high altitude, right, you actually have a lower atmospheric pressure. Okay, so normally it's 760, let's say in Utah, let's say your atmospheric pressure is like 630 torr, right? It's lower. So that means that at 95 degrees Celsius, your vapor pressure of water is equal to that lower atmospheric pressure, and then the water comes off easier, which also means that you're cooking your pasta at a lower temperature when you're at high altitude. So you may have done some backpacking and notice that stuff takes a lot longer to cook if you're cooking it in water at high altitudes. If you're trying to like make pasta or something and you're at the top of a mountain, it's going to take way longer than it would if you're just like at home in California or something on the beach. Okay, so that's kind of why all that happens. I think it's pretty cool. Hopefully you think it's cool. Okay, so everything we just went over, a lot of just like information, and honestly, most of this is like just interesting, you know, learn why chemistry is cool and important. The general idea, I think you need to pull from basically everything I just talked about, is that things boil when their vapor pressure equals the atmospheric pressure. That's the main idea. And stemming from that idea, you would know that things boil easier at higher altitudes because there's less atmospheric pressure, or things take longer to boil when there's more pressure, like in a pressure cooker. Um, those are kind of the main ideas to pull from that. So anyway, pretty cool stuff. All right, moving on. Okay, so now we're going to be talking about calculations with gases, which isn't as interesting as the applications, but still useful in problem solving. So pressure, we talked about, it comes from molecules colliding with the walls of containers, okay? And temperature is related to kinetic energy, or the speed of a molecule. So the higher the temperature, the faster the molecules are moving. And the faster they're moving means they have more force, right? So some simple physics here, force equals mass times acceleration. Okay, so if a particle is moving faster or has a higher acceleration, it's going to have greater force. Okay, and then pressure equals force over area. So if you increase the force, ooh, that's an arrow. If you increase the force, you're going to increase the pressure over a certain, if it's over a fixed amount of area. Okay, so that just all that to say, increasing the temperature increases the pressure. Decreasing the temperature decreases the pressure. So we can say that pressure and temperature are proportional to each other because of that. So Guy-Lussac's law. This is the law that relates pressure and temperature, okay? And what it says is basically, because they're proportional, you can say the pressure of a gas and the temperature of a gas at one point is going to equal the pressure over the temperature at another point. Basically, there's going to be a lot of equations and a lot of names of different laws, like Boyle's law and Charles' law and all these different things. And really, they're just going to be relating two different variables. So it might be pressure and temperature, or pressure and volume of a gas. You can write these down. I'm going to show you the ideal gas law, which we're going to get into next. Sorry to keep you hanging, but the next lecture talks about the ideal gas law, which is PV equals nRT. Using this gas law, you can get to all of these other laws, okay? So if you just remember this, which I believe is on the equation sheet for the exam, so you don't even have to memorize it, you can basically get to all the other ones. So if we looked at, and I'll show you this with all the different laws. So PV equals nRT, okay? So basically, when we're solving a question, when we're solving a question about gases that only deals with pressure and temperature, we're going to assume that everything else is constant, okay? So if everything else is constant, we're going to say, we can rearrange this equation to say P over T equals NR over V, okay? And since these are constants, let's just replace it with a variable, we'll say Z, okay? So we're going to say P over T equals Z for a certain gas if it has a fixed volume and a fixed number of moles. R is called the gas constant, and so it's just a number. So that number never changes anyway. Okay, so P over T equals Z, okay? Which means that you could say P over T at one point is also going to equal P over T at another point, as long as the volume doesn't change and the number of moles of the gas doesn't change. N equals the number of moles of a gas, okay? And again, we're going to have some practice with this as we learn these other laws. But now you can kind of cut out this middle part, and you can see that P1 over T1 equals P2 over T2, okay? And that's this law right here. So using this, you can basically get to all the laws. If you don't like math, derivations of equations, then sure, you can just measure it or memorize it if you want. It's up to you. And then you can, of course, rearrange it to get to whatever you need to, whenever you need to. Okay. And again, temperature must be in Kelvin in all these gas equations that we do. Kelvin to, or Celsius to Kelvin is a pretty simple conversion. Okay, we take the Celsius temperature and you just add 273.15 and you get the Kelvin temperature. Okay. All right, so let's see an application of this law. So you fill a basketball with air on a cool summer morning when it's 20 degrees Celsius. Okay, fill it to a pressure, let's see. Okay, to a pressure of 22.7 psi. Okay, so when you're looking at these, the P1 and the T1 are going to represent your initial pressure and temperature. So our initial pressure is 22.7 psi, and our initial temperature is going to be 20 degrees Celsius, which is actually 293.15 Kelvin. Okay. All right. Later that afternoon, the temperature is 32 degrees. What is the pressure inside the basketball? Okay. So we're going to be, since this problem is only dealing with pressure and temperature, we have P1 over T1 is equal to P2 over T2. And it's asking what is the pressure inside the basketball later in the afternoon. So what we need to solve for is P2. So you could rearrange this equation. So basically, if you multiply both sides by T2, maybe I'll just do it over here. Multiply both sides by T2. You're going to get T2 times P1 over T1 equals P2, right? That's the equation. Again, for all these, you're going to assume that the volume of the gas hasn't changed and that no gas has come in or out, right? You have to keep a constant volume and a constant number of moles for this to work. Rearrange the equation to get here, okay? Is that what I got? Oh yeah, same thing I got, it's just kind of written differently. Okay, so our initial pressure is 22.7 psi. Oh, sorry, that's our final, yeah, that's our initial pressure, right? It's P1. Final temperature, or the temperature in the afternoon is 32 degrees, okay, which is 305 Kelvin. 20 degrees converts to 293 degrees Kelvin. So you get 305 Kelvin over 293 Kelvin. So our P2, so the pressure in the afternoon is 23.6 psi. And we learned that when temperature goes up, pressure goes up. So you could check this if you want and say our initial pressure was 22.7 psi, and as it got hotter, it went up to 23.6. Sorry, so that makes sense. If this was lower, you would know that you did the question wrong. You'd probably want to try again. All right, go ahead and pause the video and try one of these problems on your own. All right, here we go. So we have a container of hot food is sealed and placed in a refrigerator. So that's the sealed part. Whoops, dropped my pen. The sealed part is basically telling us that we have a constant N, right? A constant number of moles because it's sealed. The gas can't get in or out. And placed in a refrigerator. If the air in the container was initially 100 degrees Celsius and 760 torr, what is the final pressure when the container is cooled to 200 degrees Celsius? Okay, in order to do this problem using Guy-Lussac's law, we also need to assume there's a constant volume as well, okay? And although this doesn't tell us that, if the problem's only giving you pressure and temperature, you're going to just kind of assume it's constant, because if they don't tell you how it changes, then there's no way to solve it if it wasn't constant, if that makes sense. So you would assume this is a container like like one of those Tupperware containers, right? That it's probably not going to change in volume when it goes in the fridge or the freezer. All right, let's see. Oh, refrigerator. Okay. So what is the final pressure when the container is cooled to 2 degrees Celsius? Okay, so we're trying to find out final pressure. So again, we're looking for P2. Let's see. Okay, we're looking for P2. So if you rearrange this equation, you would get this. You could just leave it like this and try and solve it after you plug in the numbers. It's up to you. Okay, so we have our initial pressure, which is 760 torr, which is before it was put in the fridge. Okay, and then we have our initial temperature, which is T1 down here, 373 Kelvin. That's 100 degrees Celsius, right? And then it's cooled down to 2 degrees, which is 275 Kelvin, which is that number right there. Okay. And you just plug it in the calculator and solve it, basically. That's all you're doing at this point. So there we go, 560 torr. Okay. We're going to get into this a little bit more in the next lecture. But hopefully that gave you a decent foundation, because these problems really aren't too bad if you have that foundation. It's a lot of the same stuff kind of repeated with different applications. So if you're doing the homework and you feel totally lost, my guess is that you're just having a hard time making the connection and understanding kind of like the root principle. So as always, come to office hours and we will go over it until you figure it out, okay? All right, we'll see you next time.